let's try with the example on page 27, right? So that is this example. This is the example, right? These three things are to be followed, right? The example is this. See, so you have this net reaction. The net reaction is this: two of NO2 gas reacting with F2 gas to give you the two of NO2F, right? This is your oral reaction. Actually, that guy is with yeah. We have to come up with the delta HR here. We don't know. We need to come up with that thing correctly before drawing the energy profile, right? Let's discuss about that thing. And then they are saying this oral reaction is actually happening with two steps. The step 1 and the step 2. Two steps are given. Right? The first step involves the reaction of NO2 gas with the F2 gas, forming the NO2F and the F gas. Second step, at the second step, the NO2 gas reacting with the F gas to produce the NO2F again, right? They are saying that this one is low, means it is the RDS, right? And they are saying this one is up, right? So that mechanism is also given. They have given you the mechanism, right? And they are now we are trying to come up with the correct energy profile for this kind of reaction and this kind of mechanism, right? Okay, let's start drawing the energy profile by following these three things one by one, right? First thing to follow this, actually, we have to come up with the correct energy levels, right? See how to do that, right? It's like this. This is the energy profile. Right? This is your energy profile, right? When it comes to energy profile, right? The two coordinates should be marked, two axes should be marked, right? So here you have the energy, here you have the energy. You can mark that thing with kilojoules or kilojoules per mole, no worries. Kilojoules or kilojoules per mole, right? And here you have the reaction pathway or the reaction coordinate. Reaction pathway or reaction coordinate. Right? Those are two axes, right? Okay, then let's first try to come up with the correct right energy levels. See, it is like this. First of all, right in the energy profile, first of all, you have to come up with the delta R of this reaction. First of all, you have to decide whether this reaction, the oral reaction, is kind of an exothermic reaction or an endothermic reaction. That is the first thing to decide before we are to draw the energy levels, right? Okay, so first come up with that by seeing the delta H naught F values given, by seeing those values, right? They have given. You can clearly see they are saying that this NO2 guy is with 34, this guy is with 34, and this the other guy is with 109. Those two values are given. So you clearly see, right, as fluorine carries zero, fluorine carries zero enthalpies because those the fluorine is kind of reference form, right? You clearly see, right, your enthalpy decreases going from reactant to products, right? Going from reactant to products, your enthalpy decreases, right? So delta H naught R. So you are starting with 30.2 and you are ending up with 1092, right? If you are to calculate the delta H value, it will be a minus value. It is like 2 into 109 minus 2 into 34, right? That is your equivalence of product minus the reactant. So you will get a minus value. So this is kind of a minus, right? In this case, it is a minus value, so it is a exothermic reaction. So this is the first thing, right? You have to come up, right? When you are supposed to draw energy product, first you have to decide, or they have to give whether the overall reaction is exothermic or endothermic. That is the most important thing first to decide. Yes, that is exothermic, right? We have decided that thing according to the definition of equivalence, right? Okay, this is the exothermic reaction, right? Okay, then let's try to come up with the energy levels, right? Energy levels, right? First, first of all, draw the energy levels of the reactants and the products of the overall reaction. This is how we do. First, draw the energy levels of the overall reaction. Don't look at any of the steps here involving in the mechanism. Just draw the two energy levels for the reactants and the products, right? Okay. So you clearly see this is an exothermic reaction. That means, right? The reactants should have a greater enthalpy, greater energy, and the products should have a lower energy, right? This is kind of exothermic. It means energy is released when going from reactor to products. That means at start you should have a greater energy. At the end you should have a smaller energy, right? So that is how the exothermic things process, right? Exothermic from reactor to products, you are releasing energy. So you are coming up with low energy state as products, right? Okay. First thing is to come up with the reactants and the products, right? Reactants and the products, and then label the species there. Label the species at those two energy levels, reactants and the products, right? Actually, now I'm drawing the energy levels. Drawing the energy levels means actually drawing the enthalpy diagram. That's it. Same as that in this these energy profiles, right? Drawing energy levels means actually drawing the enthalpy diagram, right? That's it. So at the start and at the end, and remember when drawing the enthalpy diagram, right? With each and every state, each and every energy level, the mass should be conserved and the charge should be conserved. That is something we had followed when drawing enthalpy diagram, right? The same rules are applied here as well, right? So first, draw the two energy levels of the reactants and the products. So we are to start with two of NO2, gas. It is essential to come with the physical states plus F2 gas as the reactants, as a reactant. Then as products, you have two of NO2F gas. First, write the reactants and the products with their energy levels, right? So we are still at the first step, right? Drawing energy levels. Okay. This is done with the use of the overall reaction, right? Then next one, right? After that, after writing the reactants and the products, the energy levels of those two, we are supposed to come up with the intermediate energy levels, intermediate states and their energy levels, intermediate states and their energy levels, right? How to draw that? It is like this. I have earlier said with the last lesson, I have said always the intermediates are less stable than the reactants and the products of your overall reaction. Right? Always the intermediates are less stable than the reactants and the products of your overall reaction. Right? That is understood, no? Intermediates last for a very small time, right? They just produce and just consumes completely. That is how. That is why we call such fields as intermediates. But very little lifetime is there. That means their stability is low compared to the reactants and the products of the overall reaction. So when drawing the intermediate state, as they are with lower stability, they should be with a higher energy than the reactants and the products. Low stability means high energy. High energy means low stability. That is the idea. When you have more energy, you are not that much stable. You tend to react more, with more energy, right? You tend to come some changes. So stability is low, right? So higher energy stability is low. That means as the intermediates are less stable than the reactants and the products, the energy of intermediate state should be greater than the energy of the reactants and the products, right? That is the idea. So that you have to draw the intermediate state, right, with a higher energy than the reactants and the products. Than the reactants and the products of the oral reaction, you have to write the intermediate state with a higher energy. So this intermediate state should be with a greater energy than the reactants and the products of the oral reaction, right? Okay, oral reaction reactants and products දෙන්නටම වඩා energy එක වැඩි වෙන්න ඕනේ ඔයාගේ intermediate state එකේ. Very essential. Yeah. Keep in mind. Always the intermediates are with greater energies than the reactants and the products of the oral reaction. Why is that? Because the intermediates are less stable than the reactants and the products. Very little lifetime is there. That means stability is low. Right? Okay. This is your intermediate state. This is your intermediate state, right? Intermediate state. Now, we are supposed to come up with the chemicals here. We are supposed to come up with the chemicals at the intermediate energy level, right? Let's write the chemicals at the intermediate energy level. That is not hard. Very easy to write the intermediate chemicals at the intermediate level, right? So it is like this. What you need to do is just consider the first step. Just consider the first step of the mechanism. To come up with the first intermediate state, you just consider the first step of the mechanism, right? That is needed to come up with the intermediate of the first intermediate state, right? Okay. So what it is saying? It is saying that when you are looking at the step 1, it is said that one NO2 molecule reacts with one F2 molecule to form the NO2F and F. So one NO2 molecule and F2 molecule converts to NO2F and F. Here you have two NO2 molecules. You have two NO2 molecules, but only one NO2 molecule is involved in the reaction at the state 1. So the other NO2 molecule is remaining. The other NO2 molecule is remaining unreacted. First write that thing. First write the unreacted species at the first step. So you have started two NO2 molecules. The oral reaction says like that. You have started two NO2 molecules, but only one NO2 molecule has reacted. So one guy is there without reacting. First, just write that species, the unreacted species, there. Then the other NO2 molecule and the F2, one is unreacted, the other NO2 molecule and the F2 converted to NO2F and F. So that instead of the other NO2 molecule and the F2, you just write the two products here. NO2F and the F. Right? So that is how you are supposed to come up with the intermediate state. Very easy, right? You don't write only the intermediate. Don't write only the intermediate at the intermediate energy level. That is wrong, right? The energy levels are actually the kind of enthalpy diagram. So the mass and the charge should be conserved throughout all these energy levels. Remember that. So that you are not supposed to write only the intermediate at the intermediate energy level. Right? Intermediate energy level like intermediate විතරක් coming about. The unreacted species are also there. Right? So intermediate energy level means, right, the energy at the energy of the species at your flask when the intermediate is existing there. This represents the energy, right, of the species at your flask when the intermediate is there. When the intermediate is there, not only the intermediate is appearing in the flask, some other species are also there. Some other species should be there to react with the intermediate to consume that thing afterwards. Definitely should be there. So you have to compete all the other species they are with the intermediate, right? When writing the species at the intermediate energy level, right? It's not hard, right? Very easy. But I have said goes just come with the first step of the mechanism. Then first identify the species not reacted. So you have two of NO2s and one F2. But here only one NO2 is reacted. So that means that the other NO2 is remaining. So that first write that thing. So instead of the reacted species, just write the product. So the one NO2 and H2 is reacted. So the are reacted. So instead of those, just write the two products given in the first step. So that is your intermediate step, right? Then if you have written the intermediate step correctly, right? The second step should be also right fulfilled with this diagram, right? If you have written the intermediate step correctly, right? Intermediate engineer correctly, you should be able to come up with the right second step as well, right? With this diagram. See whether it's happening or not. So at the second step, what happens? This so remain NO2 and F. These two guys will react to come up with one NO2F. So these two guys will form one NO2F, and the other remaining NO2F will give you the two NO2Fs. Got the idea? So at the second step, what happens is NO2, one NO2 is one NO2 and F will react to give you the NO2F name. So that you clearly see these two guys, one NO2 and F. Those two will react to give you one NO2F. And so remained in node 2f is also there, so that is also appearing here. So that is how the two in node 2f molecules are there at the end. See, if you are, have written the intermediate level correctly, right? Definitely, it should be okay with the second step as well, right? So that is how we are supposed to complete the energy levels, right, of our energy level diagram. That is just like a enthalpy diagram or energy level diagram, what we have drawn or what we have learned in energetics, right? In energetics, we have learned how to draw the enthalpy diagram, so energy level diagram, right? This one is the same, these energy levels are the same energy levels, right? Okay, got the idea? That is done, right? If you have any question, just ask before going to the next two steps, right? This is the first step to first thing to do when drawing any detailed diagram. Any questions there? ഇതിനിടെ അത് reaction pathway, reaction pathway drawing the reaction pathway. Next step, right? Okay, drawing the reaction pathway is very easy. Drawing the reaction pathway is very easy. We had done the hardest stuff at the beginning. अभी हमारे drawing the reaction pathway is very easy. What is the idea there? The idea is the rate determined step or the server step should come up with the greatest activation energy. That is the idea, right? When drawing the reaction pathway, okay, but when that thing, this is nothing, right? Reaction pathway again. Drawing the reaction pathway is very easy. The thing to follow, the thing to consider there is you have to draw the server step with the greatest activation energy. That's it. Last week we discussed why the source state carrying the greatest activation energy, right? So the source state should carry the greatest activation energy. The other fast steps should have some lower activation energies than the activation energy of the source state, right? That is the only thing what we need to consider when drawing the reaction pathway. But the idea, the source state should have the greatest activation energy. That's all, right? Okay, so this is the source step. This is the source step here. So that thing should be with the greatest activation energy. The first step should be with the greatest activation energy. First step should be with the greatest activation, right? Okay, the idea is that. So let's draw. First step should be with the greatest activation engine, right? Okay, I'm drawing. So just right. So this is the first step. This is the first step, right? So this is the activation energy of that thing. Just write it as EA1, EA1. Now it's better to write the chemical species at the bottom of the line. Then it won't disturb with your reaction path. Just write the chemical species bottom of the line, right? So no need to this for the reaction path, right? So this is the activation energy of the first step. This is the activation energy of the first step, right? So activation means what? Activation energy means the energy difference between the reactants and the peak of the path state. That is activation, right? The energy difference between the reactants and the peak of the first state. That is the activation energy of the first state. Activation energy of the second state means, right, the height, right, between the reactants and the peak of the second state. These are the reactants, and this is the peak. The difference here is the activation energy of the state 2. This one should be greater than this one. Why is that? Because the first step is your predetermined step, the first step. Third step carries the greatest activation energy. That is that, right? So this is your energy profile completed with the reaction pathway, right? So your energy profile is almost done, right? You have completed two steps, right? Here. Right? Okay. So those are done, right? That is okay, no? Drawing the reaction path is very easy. What you have to consider is you have to draw the right source step with the greatest activation energy. That's it, right? Okay. We have done with the second consideration of drawing an energy profile. Right? No? Fine. අපි යමු ඊළඟ කාරණේ. Right? Next one. Now we are to write the activated complex. Next thing is to come up with the activated complex. Right? අපි activated complex එක අනිත් දැන් කියනවා. Right? See, this like this. So we have two activated complexes appearing in this mechanism. The activated complex are the chemical species which appears at these peaks. Those are highly unstable. Those are the highest energy species, right? You can see in your reaction result, right? Those exist the varying minimum time, right? Okay, so the two peaks are there. So activated complexes are the chemical species, the chemical nature of the chemical species at here and here. This is the activated complex 1, and here you have the activated complex 2, right? Okay, now we are going to draw or we are going to come up with the activated complexes of this energy profile, right? Okay. So when drawing the activated complexes, right? Actually, what we are doing is, right? Right? We are to mark the right weaker bonds. We are to mark the weaker bonds, right, with dotted lines. with dotted lines, dotted longer lines. We are going to mark the weaker bonds in your activated complex in dotted longer lines. All the other bonds are going to be marked as normal, right? With normal lengths, right? With some normal nature of covalent bonds, right? So those are going to be marked like that, right? Anyway, so the major thing here to consider is we have to mark the weaker bonds in dotted longer lines, longer dotted lines, right? So what are the weaker bonds then? The weaker bonds in an activated complex, what bonds are considered as weaker bonds? The bonds which are to break and which are to form, right? When going from reactant to products in a state, when going from reactants to products in a single state. These are the two statements in first state, when going from reactant to products, right? Some bonds are to be broken and some bonds are to be formed. That is how a reaction occurs. Some bonds will break and some bonds will form. So at the first step, the bonds which will break, right, and then the bonds which are to form are the weaker bonds. So we are going to mark them in longer dotted lines. The bonds which will form and the bonds which will break will be marked in longer dotted lines. The other bonds, the bonds which are not going to form or break, will be marked as a normal covalent bond, right? Let's draw the activated complex one, then you will get a clear idea what I have just said, right? Okay, see, drawing the activated complex one. We can mark it as activated complex 1 equally AG1. This is activated complex 2, AC2, right? At here the AG1 appears, at here the AC2 appears, right? So let's draw the activated complex 1, right? So activated complex 1 is this AG1. See, this is AG1. Right? Drawing the activated complex 1, right? It's like this. I will get another one. AC1, AC2. Okay, activated complex 1. So it will be marked like this. First, in a rough paper sheet, just draw the reactants and the products. Just draw the reactants and products of the step 1. If you are trying to come up with the activated complex 1, just draw the reactants and products of the step 1. See, NO2. NO2 is this. NO2 is this. Right? This is NO2. No need to drawing all the electrons, don't pairs. Just draw the bonds. Right? This is NO2. Right? And you have H2. This is H2. NO2 and H2. And you are supposed to come up with what? You're supposed to come up with NO2F and F. NO2 and F and F. So to come up with NO2F and F, to come up with the NO2F and F, what should happen to these two guys? What should happen to these two guys to come up with these two products? So you have to make a new bond. You have to make a new bond here. You have to make a new bond here to form the NO2F. You have to break this bond. You have to break this bond and you have to form a new bond here to copy the NO2F and F. See? Right? So just draw that in a rough paper sheet. If you are supposed to complete the activity complex 1, just consider step 1. And there you get the activity complex 1, right? This is step 1. At the step 1, you get the activity complex 1. At the step 2, you get the activity complex 2. So if you are supposed to come up the activity complex 1, what you need to do is just right come up with the two reactants of the set 1. Right? I have drawn these black colored things. Then look at the products of the step 1 and see what bonds are to break and what bonds are to form to come up with those products at the step 1 for the activated complex 1. See, if you are to form a bond from here and if you break this bond, you will come up with the NO2F and the see And when drawing that activated complex, what we are doing is these two bonds, the bonds form and the bonds break. We have to mark these two in lower dotted lines. The other bonds will be marked as normal. See, it is like this activated complex binding is to oxygen, two bond, nitrogen, O minus, plus is there, okay. And this is some bond which is to form marked in lower dotted lines. F is there. This is the other bond which is to break. So the bonds break and the bonds form should be marked with lower dotted lines. Right? So this is the bond break. Bonds forming. These are the bonds or the bond breaking. Those should be marked with some lower dotted lines. Bonds forming and bonds breaking should be marked with lower dotted lines. And that is how we are supposed to come up with activated complexes. That is activated complex 1, right? Clear? Let's draw the activated complex 2 as well. The activated complex 1, right? Let's draw the activated complex 2 as well. Do you know? See? AC2. Let's try. So first draw the two reactants. First draw the two reactants. Right? First draw the two reactants of the step 2. As we are going to copy the activated complex 2, first draw the two reactants of step 2. Right? What else? Right? NO2 and F. NO2 and single F, right? So NO2 is like this. And this is right. NO2 and F, right? Then look at the product. Look at the product, and then see what bonds should be broken and what bonds should be formed to copy the product. So it is the product is NO2F. So no need of bond breaking. Just this bond forming will give you the NO2F. If you are to just form this bond between the N and N, you get the NO2F. So that is your activated complex. This should be marked with the lower red lines. So this is the activated complex 2. The bonds breaking and bonds forming should be marked with lower red lines. Right? Bond forming is your activated complex 2. Good idea, right? That is how we are going to come with the activated complex. Right? So we are done. We are done with the agent file. Good idea. Alright. Now I set up make a pivot and the gun it passing on I set up extend karana. Just complete you have space there at the page number 28. Right? There's space to draw this draw this agent file. Just draw this one. And after that I'll explain the thing again. Right? Always you are expected to come up with the physical states here. If you have not written the physical states, you won't get marks, right? Always the physical state should be mentioned with the chemical species at the end of it. If you are unable to write those things, you won't get marks. The total profile is wrong then. You don't get any marks, right? If you haven't written the physical state, right? Keep it in mind. It's very essential to come up with physical state. Just as the inter diagram, just as in an inter diagram, right? You have to mention the physical states. You have to follow the mass conservation as well as charge conservation, right? In this in the energy diagram, energy factor. Yeah. All right. Okay. Let's try to draw the second profile. අපි දෙවෙනි profile එකක් මෙහෙම අඳිමු. හරි මේ මම ආයෙත් explain කරන්න කොහොමද කියන්නේ නැහැ මොකද මේ අපිට second profile එක අඳිද්දී ඒකම ආයෙත් repeat කරන නිසා මම second page profile එක මේ දිනවලත් මතක් කරන නිසා මම ආයෙත් repeat කරන්න වෙන හැම එක right මේ and you can even watch the video as well in our video as well this thing is there so if you didn't come across any of the parts here right unable to understand right so you can go to the video again and see what things I have mentioned there right so I'll go with the second page profile right the same theories are applied again and again all things have been discussed now right I'll go with the second example as well to cement these ideas right okay right so let's come up with the second one, right? Second engine profile, right? Second for the mechanism given in page number 29, right? For the mechanism given in page number 10, let's try to come up with the engine profile, right? If you have unable to write copy the theme, just take a screen capture, right? That will be also helpful to complete the stuff, right? Okay, and go through the video once again, right? So you will get the idea clearly. Right? Okay, let's come with the next example. It is on the page number 28. Let's try to come up with the identifier for that mechanism as well, right? Okay. So first of all, before going for that, if you have any problem, any questions in this one, if so, just feel free to ask. Brush up in our hand. Hri එහෙනම් අපි යමුද next example එක කරලා මේක idea එකට පස්සේ කියයි. So next example. This is the example at the page number 29. Page 29 වල example එක කතා කරමු. So example number 2. This is the mechanism. This is for the mechanism at the page number 29, right? Right. So it is like this. The overall reaction is like this. The NO2 gas reacting with CO gas to give you the NO gas and CO2 gas. Right? This is the overall reaction and delta H value should be calculated, right? If not, you are unable to compensate the internal final state, right? The energy levels which is higher than the other, right? You can't decide that without the sign of the enthalpy change, right? Energy, right? So they have given the values, right? For these ones, right? So they have given NO2 as 33.2 and CO as minus 109. So NO as 90.3 and the CO2 as minus 393.5, right? So clearly you see the enthalpy decreases from going from here to here, right? You can calculate delta to R, right? You can calculate delta to R, right? You can calculate that value. That will be a minus delta to R is going to be a minus L, right? Yeah, you can apply the equation, right? Delta to R is right delta of F of products minus delta of F of reactants. So this is a higher negative value than this. So you come up with a negative value, right? Okay. This reaction needs to be right. Okay, the delta of F is minus, right? So when it comes to oral reaction, right? Oral reaction, it is negative, right? See, let's come with the two. Let's come with the initial and final with use of this. Let's come with the initial and final state with use of this oral reaction. So oral reaction is the one to consider to draw the initial and final elements, right? So initial and final, initial and final with and negative relation are so it's a kind of exothermic value. So the energy of the final state is less than the energy of the initial state, like that. Why is that? Because this is kind of a exothermic value, right? So energy decreases. Some energy has been released means the energy of the system decreases, going from reactor products, right? So product state should be at a lower energy level than the reactants because the overreaction is exothermic, right? So reactant state and product state will be written with use of overreaction, right? So what are the reactants and what are the products? The reactants of the overreaction is NO2 gas, NO2 gas plus the CO gas. The products are NO gas plus the CO2 gas. First, write the energy levels of the reactants and the products by just looking at the overall reaction and its enthalpy change. Right now, okay. Then we are supposed to come up with the intermediate state. Remember, always the intermediate energy level is with a greater energy than the reactants and the products of the overall reaction. Always the intermediate energy level is with a greater energy than the reactants and the products of the overall reaction. That is right, because it is less stable than the reactants and the products, right? Okay, so to come up with this intermediate energy level, right? To come up with this chemical species at this intermediate energy level, right? You need to right consider the first step to come up with the first intermediate, right? You have to consider the first step of the mechanism. See what it is. The first step of the mechanism. First step of mechanism. It says it is like NO2, two of NO2. You have two of NO2s, right? Yeah. Two of NO2s giving you NO3 gas plus NO gas. That is the first step. And the second step is actually NO3 gas plus CO gas giving you the NO2 gas and the CO2 gas. Those are the two steps, and they have mentioned that the first step is your predetermined state. Why is that? Because it is the slow state, right? That is mentioned, and this time is power. But anyway, let's first try to come up with the intermediate, right? First try to come up with the intermediate energy level. So how to draw that? How to come up with this chemical species here? What I have said is actually consider the first step. Consider the first step. And first write the reactants which are not involving. First write the reactants and first write the chemical species here which are not involving in the first step. Which is here at the oral reactants, but the species not involving in the first step should be written here, right? Those are not involving, right? So what are those, right? Here clearly you see, right? CO is not involving here. CO is not involving here. So write the CO. Write the CO. Write the CO. CO is not involving at the first step. So that is not reacting, so that it will be there at the, as a product after the first step as well, right? CO gas, right? Then that is done. Okay. Now we are supposed to complete the conversion, right? So here it says two of NO2s are to get converted to NO3 and NO at the first step. But we have a problem. What is the problem? We have only one NO2 molecule here. But they are saying at the first step, two of NO2s will get converted. So what to do? Just put two here. Without two NO2 molecules, you can't come up with the NO3 and the NO. So just put two here. That means if you have done some change to this step, definitely you have to do a change to the steps earlier balanced. You have earlier balanced this step, so you have to come up with some NO2 there as the here, here. I mean NO2 here, right? Why is that? Because I have added by hand, I have added some NO2 here to copy 2. So you have to put that same NO2 the steps we have balanced so far, right? Okay, right. So then do the thing. So here we see two of NO2s will get converted to NO3 and NO. So that instead of two of NO2s, we can write the NO3 and NO as the product of the first step. Put there, right? See, CO is not reacted. So just write that thing. After that, two of NO2s are in body at the first step. We had only one. So just put another NO2. As we had done some change to a step already balanced. So you have to put that thing you have to put by the hand to the other balanced step as well. After that, your two NO2 guys get converted to NO3 and NO. So that instead of two NO2, you can write the NO3 and NO as the product state. Right. Okay. That is done. So if you have done this correctly, if you have done the things, if you have written the things correctly at the intermediate energy level, you should be able to come up with the second step as well. See, NO3 and one NO3 and CO will give you NO2 and CO2. See, that is what happens here. One NO3 and NO. This guy gives you NO2 and CO. NO2 and CO. Right? The other unreacted, right? NO3 and CO, sorry, NO3 and CO, sorry, NO3 and CO, your NO3 and CO converted to NO2 and CO. So unreacted NO gas is still appearing as it was there, right? Then the CO into NO3 into converted one. NO2 gas CO2 credit. Or reactor nanti NO gas. So that would be best. If you have done that thing properly, if you have done this thing properly, that thing will give you the second step clearly without adding or removing any of the chemicals. Without adding or removing any of the chemicals for this stage as well as this stage, you should that should be give you the second step. If you have correctly written the chemical species at the intermediate state, right? Okay. Right. So the energy changes, energy states are done. Right? Energy levels are done. Okay. First step is done. It is done. Right. Then, then we are supposed to, then we are supposed to come up with the reaction pathway. It is very easy. Proving the reaction pathway is easy. What to do? Just, just take the source step. Just take the source step and come up with the highest activation energy for that source state in your reaction pathway. So you have to count the reaction pathway in a manner where the first step counts with the greatest activation energy. So this is the first step. This is the first step. That current activation energy EA for the first step should be greater than the activation energy of the second step. So it could be like this. The activation energy of the second step. Activation energy first step should be greater than the activation energy of the second step. Why is that? Because the first step is so predetermined step. Also, so step should come up with the greatest activation energy. That is the idea. Right now. Okay. That is the condition of the reaction count. Done. Right. Next thing is to come up with the current active electrons AC1 and the AC2. Active electrons 1 and active electrons 2. That is the next idea. Let's come up with the active electrons 1, AC1, active electrons 1. What I have told you to do, when drawing the active electrons 1, see, first consider reactants of the first step. Active complex 1 involves when the reactants of the first step converts to the products of the first step. When reactants of the first step converts to the products of the first step, that pathway is going through the activation complex 1. So activation complex 1 involves the reactants and the products of the first step. Right? So let's write the reactants of the first step and see what bonds are to be broken and what bonds are to be formed to give you the products of the first step, right? See, you have two NO2 guys, two NO2. These are NO2s. Two NO2s are there. And you are supposed to come up with NO3 and NO. NO3 and NO. You are supposed to come up with NO3 and NO. So to build the NO3 and NO, what should happen? You have to break this bond. You have to break this bond to come up with NO. To come up with the NO3, you have to form a bond from here. See? Got the idea? If you are to form a bond from here with this nitrogen and this oxygen, you get the NO3, NO3. And if you break this bond from here, you get the NO. So those are things should happen to come up with active complex 1. Then just draw this thing. So active complex 1 is this. The bonds to form and bonds to break should be written with some length yellow lines. So this is kind of a bond. This is the bond diagram, right? Here. To form. And this is the bond to break. This is the bond to break, right? This is the bond to break. Right? So if you can draw this stuff like that. No, what is it? Again, bond එක මේ පැත්තෙන් දැම්මත් කමක් නැහැ. මෙහෙන් දැම්මත් කමක් නැහැ. No worries, right? So that is it. So you can mark this document. No worries about the charges. If you are unable to put the charges, no worries, right? About the charges, right? What should have mentioned is actually bonds to break and bonds to form in long ordered lines. Long ordered lines, right? And normally the actinic complexes are written in inside square brackets. Normally the actinic complexes are written in inside square brackets, right? That is how we normally write those things. So this is your bond forming, and this is your bond breaking. That is the actinic complex one, right? Is the actinic complex one, right? Let's draw the activity complex 2 as well. What to consider? Activity complex 2 is actually the complex formed when the reactants of the second step converts to the products of the second step. When the reactants of the second step converts to the products of the second step, the reaction pathway is going through the activity complex 2. So by looking at those two things, we have to consider the activity complex 2. See, first take the reactants of the second step, right? You have NO3. So formed NO3, right? So formed NO3 is there. NO3 is there, right? No need to put the charge, right? It is not necessary. And CO is there. Those are two reactants happening at the second step, NO3 and CO. Then see what bonds are to form and what bonds are to break to form the products of the second step to come up with the activity of this two. So if you are to form, if you break to come up with NO2, you have to break this bond, one of the bonds. And if you form, if you break that bond, and if you form this bond from here, you will get CO2. If you form this bond from here, you get CO2, and this should be broken to come up with NO2. So those are two bonds which will form and which will break. So this example that we do is 2. So this is how we are supposed to write the stuff, right? So you have to break this bond. Those should be marked with longer red lines, right? And you have to form these bonds. Remember that those should be marked with the longer red lines. Bonds forming and bonds breaking, right? So that is accurate to this 2, right? This is the bond break. This is the bond form. Remember, always you have to mark with longer lines. These bonds should be usually longer than the normal bonds. Longer than normal bonds. These are normal bonds. We can't to break or form. These bonds forming and bonds breaking should be larger than those, and should be marked with the dotted lines. These show activity of these two non-written in coordinates. Right? So we are there. Activity of this year and I want to shape it. And I have complete just complete this stuff. Written here. If you have any questions, you can ask. Right? Hello, okay, screen capture का करेगा ना? हाँ, okay, मेरी screen capture करेगा ना? तो बोल लगी page number 31 वाला दिया ना? Page number 31 वाला दिया ना? Right? Energy profile लेगा, ना mechanism में energy profile लेगा construct करना, right? Just take a screen capture from here and try to construct the energy profile for the mechanism given in page number 31. In page number 31, we have a reaction with H2 and the I2, forming the 2 of H1, HI. So just try to come up with the correct energy profile for that mechanism, which is in the page number 31. just take a screen from here, right? And just try to build up the application for the thing and the thing and everyone. Honey, I'll give 5 minutes. Try to draw the stuff, right? Then after that we'll discuss. You need to find the guy to continue. Then this marker the environment here, height to be marked in, right? That should be marked directly above the height, the peak of these hills, right? Okay. अब कल भी बाहर देना फाइल में पेज फाइल का पेज में डाली मारने की एलिमेंट right let's down for this session now. Let's discuss and let's check whether you have written it correctly or whether you have done any mistakes here. Right? Have to take color one. This is the multiplication number 31, right? Multiplication number 31, right? Okay, see, the is this, right? So they have given use the deltation of H values. We know the H2 and the I2 are reference forms. So if values are 0, then the H value of HI is given as 26.5. So clearly you see that the enthalpy is increasing here, going from reactant to product, enthalpy is increasing. So delta H R is kind of a positive value. Positive value means it's a endothermic reaction. Endothermic reaction. The energy of the energy of the products are greater than the reactants. Energy of the products are greater than the energy of the reactants. That is what endothermic means. Endothermic means heat absorbing reaction. So as heat is absorbed to the system, now at the product state, you are with a greater energy than the reactant, right? As heat has absorbed, right? So that is how this thing looks like according to the energy values, right? Enthalpy values, right? So let's start drawing the energy profile, right? Okay. First, I'm always saying that first we have to draw the reactant level and the product level, right? So if you are to draw the reactant level here, so product, the energy of the product level should be greater than the reactants. Energy of the product state should be greater than the reactants. Why is that? Because we are considering kind of an endothermic reaction. The heat has absorbed, energy has absorbed to the system going from reactant products. So than the reactants, you have a great energy in products, right? So reactants and products. The products are in, with higher energy because it is an endothermic, right? Energy increase, right? Okay, then we are going to come up with the chemical species at these two energy levels. So these two are basically written by looking at the oral reaction, right? The oral reactions, reactants, and the products. The things are written according to the oral reaction. So at the reactant side, you have a H2 molecule and a I2 molecule. H2 gas and I2 gas. Remember, it is essential to come up with the physical state, right? Without the physical state, you won't get plants, right? At the product stage, you have two of HI molecules, HI gases. So the reactant and the product's energy levels are done. But that is not all of the energy levels with this mechanism. you have to write the right energy state of the intermediate energy level as well. So when it comes to intermediate energy level, that should be with a greater energy than both the reactants and products. Intermediate energy level should be with a greater value than the reactants and the products. Even with the products, they should be greater because intermediates are less stable than the reactants as well as products. Right? Okay. Let's try to come up with the chemical species appearing at the intermediate energy level. Right? That is not going to be only the intermediate chemical species, but some other chemical species may appear at the intermediate energy level. At the intermediate energy level, right? Okay, so there are how to write this thing. I am always saying first consider the step one. Consider step one. See, first write the things here which are not involved in the reaction at the step one, but which are at the overall reactions reactant side. The species which are at the overall reactions reactant side but not involving as a reactant at the step one is remaining there still without consuming, so that should be those should be written first here. So we have H2 and I2 in the overall reactions reactant side, but only I2 is involved in the reaction. So I2 is only consuming. Only the I2 is consuming. That means H2 is not consuming. So H2 is still there without consuming at the overall reactions. Sorry, at the intermediate energy level. H2 is not consuming, right? Only the I2 is consuming at the this one, right? So just write H2, the species which are not consuming here first. Then instead of two I2 molecules, you can write the 2O5. The I2 gas is connected to 2O5. So instead of I2 gas, you just write 2O5 gas. Right? That is your intermediate energy level. So if you have written this energy level correctly, it should give you the second step without adding or removing any chemical species to these two steps, these two energy levels. See, second step says H2 gas and 2 of I2 gas. Yes, those are there. Which contain 2 of H. Those are. So if you have written this thing correctly, definitely that second step should be given by these two energy levels without adding or removing any of the stuff already written, right? So this is correct, right? So writing the energy levels correctly, that's it. We have done, right? Okay. Then we are looking for the reaction path. The second thing is to come up with the correct reaction path. When consider reaction pathway, what we need to do is just come up with a higher activation energy for the step with which is the rate determined step. So when writing the reaction pathway, what we need to do is just come up with the greatest activation energy with the reaction which is known as the slowest step, right? So in this case, the second step is your slowest step. Second step is your slowest step. So the second step should have a greater height or should have a greater activation energy than the first step. See, so I am right. If this is the activation energy of the first step, if this is the activation energy of the first step, EA1, the activation energy of the second step should be greater than that. This should be greater than this. Now I just know that thing correctly. Clearly. This thing should be greater than the activation energy of the first step. Remember, your EA2 should be greater than. The EA2 should be the larger value, not the EA1, because it is the second step is the slowest step, right? Here mentioned that thing, right? The activation energy is the energy gap between the reactants and the height of the continuous state. The first steps reactants are these two. This is the height. So the energy gap is the equation. For second step, the reactants are at this stage. This is the height at the second step. So the difference is the equation 2. Right? Okay. The EA2 should be greater than EA1 because the EA2 represent the second step represent the predefined step or slower step. Right now? Okay. That is the reaction path is done. Finally, we are looking for the activated complex. Here you have the activated complex 1. Here you have the activated complex 2. Activated complex 1 and activated complex 2. Right? First write the activated complex 1. AC1. Just not write that. What we need to do? The activated complex 1 comes up in the first step with the reactant products of the first step, right? That is where you find the activated complex 1. So consider the reactants of the first step. There is I2. Just consider all the bonds there. And then think of the products. Which bonds are to break or which bonds are to form from here to come up with the products of the first step. Yes, you clearly see, if you break this bond, you easily form the two of I gases will be formed if you are to break this bond. So your active context will be like this. So bonds breaking and bonds forming should be written with some larger total line. These are your active context, and this is your bond breaking. Right now, that is your active complex one. Very clear. Bonds to break as well as bonds to form should be marked with lower order lines. Right? Then come up with the activity complex 2. This comes with activity complex 2. It says activity complex 2 comes in the comes when the reactants of the second step. Activity complex 2 comes with when the reactants of the second step converts to the products of the second step, right? So just consider the reactants of the second step. These two. And the two of ice, two of ice, two of ice. So what they are, what is happening there? Basically, the products are two of HIs, two of HIs. You can produce a two of HIs by forming these two bonds and breaking this one. If you break this bond between the two hydrogens and form two bonds between the hydrogens and iodines, you will get two of HI molecules, right? And this bond will break, right? So that is actually comes to. So you have the bond to break between two hydrogens, and you have some bonds to form between hydrogens. The diagram is two, right? These are the bonds to form. This is the bond to break. Right? So that is the diagram is two. Alright. Lawan මේක ළමයි වගේ මොනිපොත් ප්‍රශ්නය නෑ, right? If you have written the diagram is two like this, no worries, right? No worries, right? That is also accepted, right? No worry. And so that is the completion of the angel file. We have problem. There's some little mistake there, right? I2's reference state is solid. Yes, good question. I2's reference state is solid, right? Not the gas. So we can't take this as zero. There is a mistake there, right? They have to give us the I2 value, I2 gas, the entropy value should be given. Sorry, enthalpy value should be given, right? Definitely they have to give that value, right? So with the use of that, you can come up with the digital term. Yeah, some mistake is there, right? I2 gas is there, or else you have to take this as I2 solid. Just take this as I2 solid, that is better. Coming because there could be a printing mistake, right? This take this as I2 solid, right? Take this as I2 solid. It's a printing mistake, right? So if it was I2 gas, you can't take this as zero, right? The reference state of ID is I2 solid, right? Okay. Yeah, good question. Another thing is there. Oh, that was about the earlier thing. Question was asked why shouldn't CEO bond be broken in the activated complex too? What was the case? Actually, in earlier case, Akash is asking a question that he said that in active economics 2, in the earlier case, don't we need to break one of the CEO's bonds? Yes, that is true. Yes, that is true. So carbon monoxide comes with three bonds. Carbon monoxide comes with three bonds between the carbon and oxygen. Yes, it's a very good yeah, it's a very good comment, right? Yes. So carbon monoxide comes with three bonds between the carbon and oxygen. This is about the earlier question, earlier engine profile, right? Which was at the page number 29 to 30, right? Earlier one. There we had carbon monoxide and the carbon dioxide involved. There, carbon monoxide, this is about the active complex 2 there. Carbon monoxide is with three bonds between the carbon and oxygen, but when you are producing carbon dioxide, only two bonds between the carbon and oxygen, right? So definitely there should be a bond breaking between the carbon monoxide, between the carbon and oxygen. The third bond is to break. So you can mention that thing to no worries, right? Two bonds are here and third bond is like this. The breaking of carbon monoxide can be written like this, and you can mention that thing as a bond breaking acid in the early question. Sorry for that, I have a mistake. Haven't mentioned that thing in the elevation. Yeah. Because when producing CO2, that means when producing CO2, right? There should be a bond to break. That bond between the carbon and oxygen should break, right? In CO2, you don't have three bonds with the carbon oxygen, right? There's some this stage, right? Some things, other things are getting there. You can do the stuff now, right? Okay. Any other questions? Fine. Okay, that is all about the agent profiles. And some agent profiles are there in organic chemistry as well. ළමයි homework එකට ඔයාලට පුළුවන් page number 32 එකේ agent profile එක අදින්න. Just draw the agent profile of page number 282 as well. And see the agent profiles given in the page number 33 and 34. Right? Just draw the engine profile at the page number 32 as a homework, right? For the reaction of NO creating with output, we will just draw as a number. I'll check that at the next class. At the next theory class, I'll check that. So complete that thing and come to the next theory class, right? Okay, and go to the page number 33 and 34 as well. And we'll complete the engine file at our class. The engine file at the reaction is page number 35. At the page number 35, there is a blank page. We'll discuss that thing in our theory class. Because actually, I need to see whether you are to write write these profiles correctly, right? So we'll do that thing at the page number 35 at the class. Page number 35 in the class එක කතා කරමු. ඒක මොකක්ද අපේ කාර්යයක් කතා කරනවා මේ සිස්ටම් මේ කතා වෙන්නේ. right? මතක් කරගන්න පුළුවන්. ඉතින් මේක අපි ඉදි කරමු and some homework are given, right? Homework is actually do the way engine file at page 32. Draw the engine file for the mechanism at the page 32, right? Alright? Next class එකේ ඉඳලා අනිවාර්යයෙන්ම theory class එක වලදී book එක අරන් ඉන්න සහ we will discuss some questions there as well. So bring the theory book, right? Distribute when you are coming to the next class, right? Theory class, right? That is all for the today, right? And if you have any questions, doubts, just feel free to ask, right?